Welcome to the video lecture series on digital image processing. In our last class, we have started our discussion on color image processing. So, in the last class, the topics that we have covered are the fundamentals of color image processing. We have seen what is a primary color and what is secondary color. We have seen the characteristics of different colors. We have seen the chromaticity diagram and the use of the chromaticity diagram, and we had started our discussion on color models, and there we just started the discussion on RGB color model. Today we will start our discussion with the color models. So, we will complete our discussion on RGB color model. We will also talk about the HSI or hue, saturation and intensity color model. We will see how we can convert the colors from one color model to another color model, that is, given a color in the RGB space, how we can convert this to a color in the HSI space, and similarly given a color in the HSI space, how we can convert that to the RGB space. Then we will start our discussion on color image processing techniques. So, we will talk about pseudo color image processing, and there mainly we will talk about two techniques. One is called intensity slicing and the other one is gray level to color image transformation. So, let us just briefly recapitulate what we have done in the last class. In the last class, we have mentioned that all the colors of the visible light or the visible spectrum, color spectrum, occupies a very narrow spectrum in the total electromagnetic band of frequencies or band of spectrum. And the visible spectrum, the wavelength normally varies from 400 nanometer to 700 nanometer. So, at one end we have the violet, and in the other end we have the red color. And out of this we normally take three color components, that is red, green and blue, as the primary color components, because we have mentioned that in our eye there are three types of cells, cone cells, which are responsible for color sensation. There are some cone cells which are responsible, which sense the light in the red wavelength. There are some cone cells which sense the green light, and there are some cone cells which sense the blue lights, and these lights are mixed together in different proportions in an appropriate way, so that we can have the sensation of different colors. And this is the main reason why we say that red, green and blue, they are the primary colors, and by mixing these three primary colors in different proportion, we can generate almost all the colors in the visible spectrum. Then we have talked about two different colors, two types of colors. One is the color of light, other one is the color of the pigment. Now, color of the light, as we see any particular object, we can see the color which is reflected from the object because of the wavelength of the light which gets reflected from the object surface. Now, when it comes to pigment color and a color falls on it, then the pigment color, it absorbs a particular wavelength out of the three primary colors and reflects the other wavelengths. So, the primary colors of light are really the secondary colors of pigment, and the secondary colors of light, they are the primary colors of pigment. And because of this, the colors of light, they are called additive primaries, whereas the colors of the pigments, they are called subtractive primaries. And here you can see in this particular slide that the three primaries of light, red, green and blue, when they are mixed together, then red and green mixed together form what is called form the yellow light. Then green and blue, when they are mixed together, these two form the cyan, and red and blue mixed together form the magenta. And red, green and blue, all these three colors together form what is the white light. Similarly, when it comes to pigment primaries, yellow, which is a secondary color for light, is a primary color of a pigment. Similarly, magenta, which is a secondary color of light, is also a primary color of pigment. Cyan, which is a secondary color of light, is a primary color of pigment. And here you find that when these pigment primaries, they are mixed together, then they form what are the primary colors of light. So, yellow and magenta, these two together form the red light, yellow and cyan mixed together form the green light, and magenta and cyan joined together, mixed together, form the blue light. However, all these three pigment primaries, that is yellow, magenta and cyan, mixed together form the black light. So, this is the black color. So, by mixing different colors of light or the different colors of primary colors of light or different primaries of the pigment, we can generate all types of different colors in the visible spectrum. Then we have also seen what is a chromaticity diagram, and we have seen the usefulness of the chromaticity diagram. So, the chromaticity diagram is useful mainly to identify that in which proportion different primary colors are to be mixed together to generate any color. So, if I take 3 points in this chromaticity diagram, say one corresponding to green, one for the primary red and other for the primary blue, then given any point within this chromaticity diagram, I can find out that in which proportion red, green and blue they are to be mixed. So, here you find the horizontal axis tells the red component, the vertical axis gives us the green component and the blue component. So, if I write this as x and this as y, then the green component z is given by 1 minus x plus x plus y. So, I can find out that how much of red, how much of green and how much of blue, these three components are to be mixed to generate a color which is at this particular location in this chromaticity diagram. It also tells us that what are all different possible shades of any of the pure color which are available in the light spectrum that can be generated by mixing different amount of white light to it. So, you find that we have a point of equal energy that we have mentioned in the last class in this chromaticity diagram, which is white as per CIE standard. So, if I take any pure color on the boundary of this chromaticity diagram and join this with this white point, then all the color points, all the colors along this line, they tell us that if I mix different amount of white light to this pure color, then what are the different shades of this color that can be generated. Then we have started our discussion on the color model, and we have said that color model is very useful to specify any particular color. And we have said we started our discussion on RGB color model, and we have discussed in our last class that RGB color model is basically represented by a Cartesian coordinate system, where the three primary colors of light, that is red, green and blue, they are represented along three Cartesian coordinate axes. So, we have, as per this diagram, we have this red axis, we have the green axis and we have the blue axis. And in this Cartesian coordinate system, the color space is represented by a unit cube. So, when I say it is unit, that means the colors are represented in a normalized form. So, in this unit cube, you find that at the center of the cube, we have R, G and B, all these three components are equal to 0. So, this point represents black. Similarly, the furthest vertex from this black point or the origin, where the red component is equal to 1, green component is equal to 1 and blue component is equal to 1. That means all these three primary colors are mixed in equal proportion and this point represents white. The red color is placed at location 1 0 0, where the red component is equal to 1, green component is equal to 0 and blue component is also equal to 0. Green is located at location 0 1 0, where both red and blue components are equal to 0 and the green component is equal to 1, and blue is located at the vertex location 0 0 1, where both red and green components are equal to 0 and blue component is equal to 1. So, these are the locations red, green and blue, that is 1 0 0, 0 1 0 and 0 0 1. These are the locations of three primary colors of light, that is red, green and blue. And you find that in this cube we have also placed the secondary colors of light, which are basically the primary colors of pigment, that is cyan, magenta and yellow. So, these three colors cyan, magenta and yellow, they are placed in other three corners, other three vertices of this unit cube. Now, find that from this diagram, if I join these 2 points, that is black at location 0 0 0 with white at location 1 1 1, then the line joining these 2 points, black and white, this represents what is called a grayscale. So, all the points on this particular line will have different gray shades, they will not exhibit any color component. Now, given any specific color having some proportions of red, green and blue, that color will be represented by a single point in this unit cube in the normalized form. Or we can also say that that color will be represented by a vector, where vector is drawn from the origin to the point representing that particular color having a specific proportion of red, green and blue. So, this is what is the RGB color model, and you find that from this RGB color model we can also have the cyan, magenta and yellow components by simple transformation. So, given any point in the RGB color plane, what we can do is, if I look at the different color shades on different faces of this color cube, you find that the shades will appear like this. So, in this color cube, you find that we have said that the point 1 0 0 that represents red, and you find that along the horizontal axis the color varies from red to yellow. Similarly, this is a point which is 0 0 which is 1 1 1. So, this point represents white color, and in this particular case all these color components, that is red, green and blue, each of these color components are represented by 8 bit. That means, we have altogether 24 different color shades which can be generated in this particular color model. So, the total number of colors that can be generated is 2 to the power 24, and you can easily imagine that is huge number of colors which can be generated if we assign 8 bits to each of the color components, that is red, green and blue. But in most of the cases, what is useful is called safe RGB model. The safe RGB model, in safe RGB model we do not consider all possible colors, that is all the 2 to the power 24 different colors, but rather the number of different colors which are used in such cases is 256. 216. So, these 216 colors can be generated by having 6 different colors in red, 6 different color shades in green and 6 different color shades in blue. So, we find that on the right hand side we have drawn a safe RGB color cube. So, here we find that we have 6 different shades of any of the colors, that is red, green and blue, and using these 6 different shades we can generate up to 2 to the power 16 different colors, and these 216 different colors, and these 216 different colors are known as safe RGB colors because they can be displayed in any type of color monitor. So, you should remember that in case of true RGB, though we can have total of 2 to the power 24 different colors, but all the color displays may not have the provision of displaying all the 2 to the power 24 colors, but we can display 216 colors in almost all the color displays. So, this is what is called safe RGB color model, and the corresponding cube is the safe RGB color cube. So, it is quite obvious from this discussion that any color image will have 3 different color components, one color component for red, one color component for green and one color component for blue. So, if I take this particular color image, you find that the top left image is a color image and the other 3 are the 3 planes of it. So, the red color component of this color image is represented in red, the green color component is represented in green and the blue color component is represented in blue. So, here we find that though we have represented these 3 different components in different colors, that is red, green and blue, but they are actually monochrome images, and these monochrome images are black and white images, and these black and white images are used to excite the corresponding phosphor dot on the color screen. So, the red component will activate the red dot, the green component will activate the green dots and the blue component will activate the blue dots. And when these 3 dots are activated together with different intensities, that gives you different color sensation. So, obviously for any type of color image like this, we will have 3 different planes, one plane corresponding to the red component, the other plane corresponding to the green component and a plane corresponding to the blue component. Now, as we said that this red, green and blue, they are mostly useful for the display purpose, but when it comes to color printing, the model which is used is the CMY model or cyan, magenta and yellow model. So, for the color image printing purpose, we have to talk about the CMY model. However, the CMY can be very easily generated from the RGB model. So, as it is obvious from the color cube, the RGB cube that we have drawn, and the way the CYM, cyan, magenta and yellow colors are placed at different vertices on that RGB cube. So, from there it is quite obvious that specified any color in the RGB model, we can very easily convert that to CMY model. The conversion is simply like this, that given RGB components, so we have the red, green and blue components of a particular color, and what we want to do is we want to convert this into CMY space, and the conversion from RGB to CMY is very simple. What we have to do is we have to simply make this conversion, that CMY is equal to 1 1 1 minus RGB. So, here you remember that these RGB components are represented in the normalized form, and similarly by this expression the CMY components that we get, that will also be represented in normalized form. And as we have said earlier, that equal amounts of cyan, magenta and yellow should give us what is a black color. So, if we mix cyan, magenta and yellow, these three pigment primaries in equal proportion, then we should get the black color. But in practice what we get is not a pure black, but this generates a muddy black. So, to take care of this problem, along with C, M and Y, cyan, magenta and yellow, another component is also specified, which is the black component. And when we also specify the black component, in that case we get another color model, which is the CMYK model. So, the cyan, magenta and blue, so this is CMYK model. So, cyan, magenta and yellow, they are same as in CMY model, but we are specifying an additional color which is black, giving us the CMYK model. So, you find that in case of CMYK model, we actually have 4 different components: cyan, magenta, yellow and black. However, given the RGB, we can very easily convert that to CMY. Similarly, the reverse is also true. Given a specification, a color in the CMY space, we can very easily convert that to a color in the RGB space. Now, the next color model that we will consider is the HSI color model, that is hue, saturation and intensity model. So, as we have mentioned in our last class, that both the RGB as well as CMY or CMYK, they are actually hardware oriented. The RGB color model is oriented towards the color display or color monitor. Similarly, CMY or CMYK, these two models are oriented towards color printers. Whereas, when it comes to human interpretation, we said that we do not really think of that given any particular color, how much of red, how much of green and how much of blue is contained within that particular color. But what we really think of is what is the prominent color in that particular specified color. So, which is what is known as hue. Similarly, we have said the saturation, it indicates that how much a pure spectrum color is really diluted by mixing white color to it. So, if you mix white colors to a pure spectrum color in different amounts, what we get is different shades of that particular spectrum color. And as we said that I, the intensity, this actually is the chromatic notion of brightness of black and white image. So, what we have is hue, which tells us that what is the prominent color, prominent primary color or spectrum color in that particular specified color. We have the saturation, which indicates that how much white light has been added to a pure spectrum color to dilute it, and we have this component intensity, which is actually a chromatic notion of the brightness. Okay. Now, the given problem is, given a color in RGB space, can we convert that to HSI space? Now, this HSI model has other importance also in addition to just interpretation by in addition to human interpretation, because you find that this HSI model, it decouples the intensity information from the color information. So, this I gives you the intensity information, whereas H and S, the hue and saturation together, this gives you the chromatic information. So, as we can decouple the chromatic information from the intensity information, many of the image processing algorithms which are developed for black and white images or grayscale images can be applied to this to the images specified in HSI space. So, conversion of an image from the RGB space to HSI space is very, very important. Now, let us see that how we can convert an image specified or a color specified in RGB space to the to a color in the HSI space. Now, in order to do this, what we can do is we can reorient the RGB cube, the RGB space in such a way that the black point or the origin in the RGB cube is kept at the bottom and the white comes directly above it. So, as shown here. So, we find that it is the same RGB cube, and what we have done is we have simply reoriented this RGB color cube, so that the black comes at the bottom. So, this is the black one, the black comes at the bottom and the white comes directly above this black point. So, naturally, as before, the line joining black and white, this represents the intensity axis, okay, so any point on this particular line which joins black and white, they won't show any color information, but they will have different intensities or different gray shades. Now, once we reorient this RGB cube like this, now suppose we have a color point, we have any color point specified within this RGB cube. So, I have this color point specified in the RGB space. Now, for this color point, now our aim is how we can convert this RGB specification into HSI specification. So, as we said that the line joining black and white, this line is the intensity axis. So, in the HSI space, I can very easily compute the intensity component, because for this point, say I say this is a point, say x, I can represent this point as a vector joining from black to this particular point, and the intensity component that is associated with this RGB value is nothing but projection of this vector on the intensity axis. So, if I project this vector on the intensity axis, then the length of this projection tells us what is the intensity component associated with this particular RGB specified color point. Okay. Now, to get this, what I can do is we can draw a plane, we can just pass a plane which is perpendicular to the intensity axis and containing this particular point x. So, the point at which this plane will cut the intensity axis, that point represents the intensity associated with the RGB component specified for this particular point x. So, this is how we can compute the intensity component. And then you find the next component, that is the saturation. How we can compute? So, this one tells us that what is the intensity. Now, how can we compute the saturation? Because the line joining black and white, the intensity axis, any point on the intensity axis has only gray shades, this does not have any color component. So, you can say that the saturation of all the RGB points, the saturation associated with all the RGB points lying on this intensity axis is equal to 0. and the saturation will increase as the point will move away from this intensity axis. So, keeping that in mind, we can say the distance of this point x from this intensity axis, this distance tells us that what is the saturation that is associated with the RGB components of point x. So, you can very easily compute the intensity and saturation corresponding to any RGB point given in the RGB space. Now, the next question is computation of the hue component. So, out of hue, saturation and intensity, we have been able to compute the saturation and intensity very easily. The next component which is left is the hue component. Now, for hue component computation, the concept is slightly more complicated. Now, we find that in this diagram, we have shown a plane passing through the points black, white and cyan. So, as we said that the line joining black and white is the intensity axis. So, intensity at point black is equal to 0 and intensity at point white is maximum, that is equal to 1. And the other point which defines this particular plane is the cyan, that is this particular point. Now, you will appreciate that for any points in this particular plane defined by these 3 points black, white and cyan will have the same hue, because as we said that hue indicates that what is the prominent wavelength of light present in any particular color. And from our earlier discussion, you can also very easily verify that for any point given on this particular plane defined by these 3 points cyan, white and black, for any points the color components can be specified by linear combination of these 3 points cyan, white and black. Now, because white is a balanced color which contains all the primary components in equal proportion and black does not contain any color component. So, these 2 points white and black cannot contribute to the hue component associated with this point line in this plane. So, the only point which can contribute to the hue component is the cyan. So, for all the points lying in this plane, the hue will be same and it will be same as the hue associated with this point cyan. So, here you find that if I rotate this particular plane around this black and around the intensity axis by an angle of 360 degree, then I will trace all the possible points that can be specified in the RGB color space. And by rotating this plane by 360 degree around the intensity axis, I can generate all possible hues that can be all possible hues corresponding to every possible RGB point in the RGB color cube. Now, in order to do that, what we do is like this. Suppose I take projection of this RGB cube on a plane which is perpendicular to the intensity axis. So, if I take the projection, then the different vertices of the cube will be projected on a hexagon as shown in this particular figure. So, the 2 vertices corresponding to red and black, they will be projected at the center of the hexagon. So, this point will be the projected point for both white and black. And the other primary colors of light and the primary colors of pigments, they will be projected at different vertices of the hexagon. So, here you find that if I draw a vector or if I draw lines joining the center of the hexagon to all the vertices of the hexagon, then red and green, they will be separated by an angle of 120 degree. Similarly, green and blue, they will be separated by an angle of 120 degree. Similarly, blue and red, they will also be separated by an angle of 120 degree. In the same manner, for the secondary colors, yellow and cyan, they will be separated by an angle of 120 degree. Cyan and magenta will be separated by an angle of 120 degree, and similarly magenta and yellow, they will also be separated by an angle of 120 degree. However, the angular separation between red and yellow, this is equal to 60 degree. So, if I take the projection of the RGB cube on a plane which is perpendicular to the intensity axis, then this is how the projection is going to look like. Now, along with this, you will find that the projection of the shaded plane that we have seen in our previous slide will be a straight line like this. So, for any point specified in the RGB color space, there will be a corresponding point in our projected plane. Say this is a plane corresponding to a color point in the RGB color space, and the plane on which this color point will lie, the plane defined by the corresponding color point, the black point and white point on which this point will lie, that will be projected as a straight line on this particular plane. So, as we rotate the plane by 360 degree around the intensity axis, this particular straight line will also be rotated by an angle of 360 degree around the center of the hexagon. So, if I rotate this particular shaded plane by an angle of 360 degree around this black and white axis of the intensity axis, its projection onto the plane, onto this perpendicular plane which is a straight line, will also be rotated by an angle of 360 degree around the center of this hexagon. Now, this gives us a hint that how we can find out the hue associated with a particular color point specified in the RGB color space. So, the hue can be computed like this, that the straight line, it is the angle between the straight line which is the projection of this shaded plane with one of the primary colors, and normally this primary color is taken to be red, and this angle is normally measured in anti-clockwise direction. So, using this particular convention, the red will have a hue which is given by 0 degree, and as we rotate this shaded plane around this intensity axis, this particular straight line which is the projection of it will also be rotated by 360 degree, and as it is rotated, the hue is going to be increased. So, hue is normally measured by the angle between the red axis and the line which is the projection of this plane on this projection of this shaded plane on this plane of this hexagon. Now, given these particular concepts, that is how we can obtain the hue, saturation and intensity components for any color specified in RGB color space. Now, we can find out that if you follow the geometry of this particular formulation, then we can have very easy relations to compute the H, S and I components from the R, G and B components. So, here the hue component, the H will be simply given by an angle theta, and as we said that this theta is measured anti-clockwise from the direction of red. So, this will be equal to theta if the blue component is less than or equal to green component, and it will be 360 degree minus theta if blue component is greater than the green component. So, this is how we can compute the hue component in the HSI specific in the HSI model, where the value of theta is given by cosine inverse half of R minus G plus R minus B divided by R minus G square plus R minus B into G minus B, this to the power half, where R is the red component, G is the green component, and B is the blue component of the color specified in the RGB space. So, from this R, G and B component, we can compute the value of theta following this expression, and from this theta we can find out the hue component in the HSI space as hue will be equal to theta if blue component is less than or equal to green component, and hue will be equal to 360 degree minus theta if blue component is greater than green component. Similarly, following the same geometry, we can find out that the saturation is given by 1 minus 3 divided by R plus G plus B into minimum of R, G and B, and the intensity is simply given by 1/3 into R plus G plus B. So, from this red, green and blue components, we can very easily find out the hue, saturation and intensity components. So, as we have converted from RGB space to the HSI space, similarly, we should also be convert any color specified in HSI space into the components in the RGB space. So, to do that conversion or the inverse conversion, the corresponding expressions can be found as, you find that whenever we want to convert from HSI to RGB, then there are three regions of interest. One region is called RG region, and in RG region H lies between 0 degree and 120 degree. The other region is called GB region, and in GB region H lies between 120 degree and 240 degree. And the third region is called BR region, and in BR region H lies between 240 degree and 360 degree. And here in the RG region, you find that getting red, green and blue components is very easy. What we do is simply the blue component is given by I into 1 minus S, where I is the intensity and S is the saturation. The red component is given by I into 1 plus S cosine H divided by cosine 60 degree minus H, and green component is simply given by 1 minus R plus B. Similarly, in the GB region, the first operation that we have to do is we have to modify H. So, we have to make H is equal to H minus 120 degree. And once we do this, we get the RG and B components like this. R is equal to I into 1 minus S. G is given by I into 1 plus S cosine H divided by cosine 60 degree minus H, and blue in the same manner is given by 1 minus R plus G. And in the third sector, that is in the BR region, we have to modify first H like this. H should be equal to H minus 240 degree. And once we do this modification, then the G component is given by I into 1 minus S. The blue component is given by I into 1 plus S cosine H divided by cosine 60 degree minus H, and obviously the R component is given by 1 minus G plus B. So, you find that using these simple expressions, we can convert a color specified in the RGB space to a color in the color components in the HSI space. Similarly, a color specified in the HSI space can be easily converted to color components in the RGB space. So, here in this diagram we have shown the effects of this different components H, S and I on the colors. So, in the first row you find that the first rectangle is a color for which hue is equal to 0, intensity is equal to 128 and saturation is equal to 255. So, as we said that our hue is measured from the red axis, from the red line. So, hue equal to 0 indicates that it is red color. In this case, the saturation equal to 255, which is the maximum, that means it is the pure red color, and intensity here is 128. So, for other rectangles in the same row, what we have done is we have kept hue and intensity constant, whereas the saturation is decreased. So, here we find that as we move from left to right, it appears that this red is becoming milky gradually. So, as we have saturation is equal to 200, which is less than 255, it appears that some amount of white light has been added in this particular red component, and that is very, very prominent when S is equal to 100 or even S is equal to 50, where a large amount of white light has been added in this red component. In the second row, what we have done is we have kept hue and saturation constant, that is hue equal to 0 and saturation equal to 255, and what we have varied is the intensity component or the I component. So, here we find that as we decrease the I component, the different rectangles still show the red color. As we move from left to right in the second row, they are still red, but the intensity of the red goes on decreasing. So, if you just note the difference between the first row and the second row, in the first row it appears that some white light has been mixed with the red, whereas in the second row there is no such appearance of mixing of white light, but it is the intensity which is being decreased. If you look at the third row, in the third row what we have done is we have kept the intensity and saturation constant, but it is the hue component which has been changed. So, we have started with hue equal to 0, which is red, and here you really find that as we change the hue component, it is really the color which gets changed. Unlike the previous two rows, in the first row it is the saturation or more and more white light is being added to the pure color. In the second row the intensity is getting changed, but in the third row, where keeping the intensity and saturation same, we change the hue component, it is the color itself that gets equal to changed. So, here you find that when we have hue is equal to 100, it is the green color. When we have hue equal to 150, it is the blue color, whereas when hue is equal to 50, it is a color between yellow and green. So, with this we have introduced the various color models, we have introduced the RGB color space, we have introduced the CMY or cyan, magenta and yellow color space, and also CMYK, that is cyan, magenta, yellow and black color space, and we have also introduced the HSI color space. And we have seen that given any color, given the specification of any color in any of the spaces, we can convert from one space to another. That is, from RGB to CMY, the conversion is very easy. We can also convert from RGB to HSI, where the conversion is slightly more complicated. Now, with this introduction of the color spaces, next what we will talk about is the color image processing. So far what we have discussed is the representation of a color, or the representation, and when we take an image and take the colors component, the colors present in the image, then so far we have discussed how to represent those colors in either the RGB plane or CMY or CMYK space or the HSI space. And the images represented in any of these models can be processed. So, in color image processing, we basically have two types of processing. One kind of processing is called pseudo color processing, this is also sometimes known as false color, and the other kind of processing is what is called full color processing. In pseudo color processing, as the name implies, that these colors are not the real colors of the image, but we try to assign different colors to different intensity values. So, pseudo color processing, actually what it does is it assigns colors to different ranges of gray values based on certain criteria. Now, what is the purpose of assigning colors to different ranges of gray values? As we have mentioned earlier, that if we have a simply black and white image, we can distinguish hardly 2 dozens of the gray shades, whereas in color we can distinguish thousands of color shades. So, given a grayscale image or an simply black and white image, if we can assign different colors to different ranges of gray values, then the interpretation of different ranges of gray values is much more easier in those pseudo colored images than in the grayscale images. So, we will discuss about how we can go for pseudo coloring of an image given in the pseudo coloring of a black and white image. So, as we said that this coloring has to be done following some criteria. So, with this introduction, and of course, in case of full color processing, as the name indicates, the images are represented in full color and the processing will also be done in the full color domain. So, given this introduction of the color processing techniques, the two types of color processing, pseudo color processing and full color image processing, we finish our lecture today, and we will continue with this topic in our next class. Now, let us come to some questions on today's lecture. The first question is, what is the usefulness of chromaticity diagram? How can you convert a color specified in RGB model to HSI model? Third question, how does CMYK specification help in color printing? The fourth question, which color is indicated by H is equal to 60? That is, hue is equal to 60. And the fifth question, what is the use of pseudo coloring techniques? Thank you.